So the next really big idea for our class is conservation of energy. And one way that we can frame conservation of energy is that it's the idea that energy is never created or destroyed. And so the way that we've reframed the work energy theorem into this equation here is helping us understand that idea. So what this equation says at a very basic level is just you start with some amount of energy. There's an initial energy of the system. And then based on work done by non-conservative forces, you can either add energy to your system or you can take energy away. But if you keep track of that, that's going to tell you what the final energy of your system is. So even if the total energy of your system changes, so that whatever you started with is not the same as the total mechanical energy that you end up with, that difference is not because energy was simply created or destroyed. That difference came about because of work done by non-conservative forces. And so you just have to keep track of that. This also highlights that these two different types of forces that we have, conservative forces and non-conservative forces, that the work they do serves two very different functions in terms of thinking about energy. Conservative forces, when they do work, what the work done by conservative forces does is it transfers energy from one form to another within the system. So work done by conservative forces doesn't change the total energy of your system. Instead, it converts it from kinetic to potential energy or potential energy to kinetic energy. Non-conservative forces, on the other hand, they change the total energy of your system. So non-conservative forces, when they do work, will transfer energy into or out of the system. Part of why we've given this special set of forces a different name and called them conservative forces is that the work they do doesn't change the total mechanical energy of your system. So when we take our equation, let's let the work done by non-conservative forces be zero. Then what that means is that the initial and final energy of the system has to be the same. The total mechanical energy you started with is equal to the total mechanical energy that you ended up with, which is another way of saying that the energy of your system is constant with respect to time. It doesn't change in time, which is exactly what we mean when we say the energy of your system is conserved. So when the energy of your system is conserved, work is still done, but the work is being done by conservative forces that simply transform the energy from one form, say kinetic, to another, potential, or from potential to kinetic. So just reframing this in terms of the total mechanical energy and breaking that back up into kinetic plus potential, then we can take our equation up here at the top and rewrite it as the initial kinetic energy plus the initial potential energies relative to some zero point plus the work done by non-conservative forces is equal to the final kinetic energy plus the final potential energy relative to that same zero point. And this we can think of as our conservation of energy equation. It's equally valid, and in some sense it's potentially even more valid, to think of it as an energy balance equation. But either way that you label it, the big idea is sitting right here. You start with some total amount of mechanical energy. Work is done by conservative forces to convert the energy from one form to another. Work is done by non-conservative forces to change what that total amount of energy is. And when you keep track of all that work done by both conservative and non-conservative forces, that's going to tell you what the final energy of your system is in both kinetic and potential energies. So when it comes to using this equation, our conservation of energy or energy balance equation, what we want to start by thinking about is what types of energy do we need to keep track of. And so the first one is, well, we'll keep track of kinetic energy. That's going to be energy due to an object's motion. And the fundamental question that we're going to ask to figure out whether or not we need to keep track of kinetic energy is just, does the object move? Second, gravitational potential energy. Again, this is work done by the gravitational force, And the fundamental question we'll have here is, well, does the object change heights? Does it start at some height? Does it end up at a different height? And then 3, there'll be an elastic potential energy. And so here we have the work done by a spring force. And again, our fundamental question here is, does a spring get stretched or compressed? If it does, then we know we'll need to keep track of the elastic potential energy relative to some 0 point. Now, the other thing that we want to think about, of course, is how is it in this equation that we're going to keep track of work done by all the forces? And of course, part of what we want to really emphasize is we're keeping track of the work done by 2 forces in potential energy terms. So the work done by the gravitational force, we keep track in gravitational potential energy terms. The work done by the spring force, we keep track in terms of elastic potential energy terms. What's special about these 2 conservative forces is that we're going to keep track of their work by thinking about how a potential energy changes. For all other forces, we're going to lump the work they do into the work done by non-conservative forces. So when it comes to thinking about the work terms, just like we did with the work energy theorem, we're going to keep track of the work done by gravity and a spring in terms of our potential energy. Everything else we're going to treat exactly like we did before, and just all of that gets included in the work done by non-conservative forces.